Now we formulate the general criteria for the equilibrium of a rigid body. We have already shown that a system of forces F1, F2, ellipsis, Fn applied at the points given by the position vectors R1, R2, ellipsis, Rn relative to an arbitrary point O of the body can always be reduced to two set of quantities. The first set consists of a single vector, a resultant or a net force F given by the vector sum of the forces Fi from I equals 1 to n, which is applied at the point O. The second set is a force couple producing the torque tau given by the sum of the vector products of the position vectors Ri and the forces Fi, from I equals 1 to n. The force F acting at the point O can be replaced by the force acting at the center of mass c of the body and the force couple F and minus F acting at the points O and C. Then the force couple on its own would produce a rotation about an axis passing through the center of mass c of the body, and the resultant force F on its own would produce both a translation and a rotation about an axis passing through the center of mass c. It follows from these statements that in equilibrium both the force F and the torque tau must equal to 0. We can conclude that a rigid body is in equilibrium if the resultant force F of all the forces acting on the body and the net torque tau of the torques produced by these forces with respect to an arbitrary point vanish. In that case we can say that the forces acting on the rigid body are balanced. Here we can talk about the torque with respect to an arbitrary point since we already proved that if the net force F vanishes and the net torque tau with respect to a given point is 0, then the net torque with respect to any other point is also 0. We note that the forces acting on a rigid body can be both unconstrained forces such as the weight of the body, and constrained forces, for example the support or the suspension of the body, since the criteria for the equilibrium of rigid bodies do not make any distinction between them. Now we examine and interpret the equations describing the criteria of equilibrium of rigid bodies. The first criterion of equilibrium can be illustrated by the statement that the polygon of forces constructed from the vectors representing the n forces Fi acting on the body regardless to their points of application, must be closed if the body is in equilibrium. This construction can also be done for the second criterion with the torques tau I produced by the forces Fi, where the polygon of the n vectors tau I must be closed for a rigid body in equilibrium. The two equations describing the criteria of equilibrium of a rigid body have a fundamental importance in statics. The first equation is also known as the criterion of the translational equilibrium of a rigid body, because the body either stay at rest or perform a rectilinear motion if the net force acting on it vanishes. The second equation is called the criterion of the rotational equilibrium of a rigid body, since the sum of the torques produced by the forces at any point of the body is 0 and the body is not rotating. Then we can say that a rigid body is in static equilibrium if it is in both translational and rotational equilibrium. These two vector equations can be expressed as 6 scalar equations of the components of the vector quantities in a Cartesian coordinate system. The 6 equations allow us to determine 6 unknown quantities, for example the components of forces or the coordinates of the points of applications of forces. The first 3 scalar equations describing the criterion of the translational equilibrium of a rigid body state that the sum of the x, y and z components of the forces Fi acting on the body from I equals 1 to n vanishes. The second set of the scalar equation are the components of the equation describing the criterion of the rotational equilibrium of the body. The x component of the vector equation states that the sum of the y coordinate of the point of application of the force Fi times the z component of the force Fi, minus the z coordinate of the point of application of the force Fi times the y component of the force Fi from I equals 1 to n vanishes. The other two equations for the y and z components of the vector equation can be derived by applying a cyclic permutation of the Cartesian indices x, y and z. We already determined the criterion of equilibrium for a rigid body free to rotate about a fixed axis or a fixed point. In the case of a fixed axis, the equation describing the equilibrium of the body states that the sum of the z components of the torques tau I produced by the forces Fi acting on the body from I equals 1 to n is 0, where the z-axis is the axis of rotation. This case involves only one equation, the z component of the second vector equation. In the case of the fixed point, the equation describing the equilibrium of the body states that the vector sum of the torques tau I produced by the forces Fi acting on the body from I equals 1 to n is 0. This is the vector equation describing the criterion of the rotational equilibrium of the body when no constrained forces are applied on the body, and it is given by the 3 component equations. There is no contradiction between these two cases and the criteria presented here, since the remaining 5 equations for the first case or 3 equations for the second one, allow us to determine the constraint or reaction forces when we fix the point or the axis of rotation. For example, let us consider a horizontal thin beam supported at 2 points, where the only unconstrained force acting on the beam is its own weight g, having the point of application at the center of mass c of the beam. The forces F1 and F2 exerted on the beam by the 2 pin supports at the distances d1 and d2 from the center of mass c are the constrained forces acting in the system. In a Cartesian coordinate system attached to the point of application of the force F1 where the x-axis is parallel with the beam, the y and z coordinates of the points of application of the constrained forces vanish. The x-components of the position vectors pointing from the center of mass c to the points of applications of the forces F1 and F2 are given by minus d1 and d2, respectively. Since all the forces acting on the beam are parallel with the y-axis, their x and z components vanish and their y components are equal to the magnitude of g, minus the magnitude of F1 and minus the magnitude of F2, respectively. As a result, the vector equation describing the criterion of the translational equilibrium of the beam has a non-vanishing y component stating that the magnitude of the weight g, minus the magnitude of the force F1, minus the magnitude of the force F2 is equal to 0. The vector equation describing the criterion of the rotational equilibrium of the beam has a non-vanishing z component, and it states that the distance d1 times the magnitude of the force F1, minus the distance d2 times the magnitude of the force F2 is equal to 0. The magnitudes of the two forces F1 and F2 can be expressed from these two equations as the ratio of the distance d2 to the sum of d1 and d2, times the magnitude of g, and the ratio of the distance d1 to the sum of d1 and d2, times the magnitude of g, respectively. These two equations show that the magnitudes of the action forces F1 and F2 or the reaction forces exerted on the two supports by the beam, are inversely proportional to the distances between their points of application and the center of mass of the beam. This result can also be derived from the principle of superposition of forces acting on a rigid body. We note that if 3 pin supports are applied for the beam instead of 2 supports, the constrained forces cannot be determined uniquely in the statics of rigid bodies. Such cases are called statically indeterminate structures with more unknown forces acting in the system than the available equations of equilibrium. When we talk about the equilibrium of a rigid body, we can distinguish between 3 different types of equilibrium. Let us suppose that a rigid body is in equilibrium, that is, the forces acting on the body are balanced. When displaced from equilibrium, the body will change its position, and the net force of the forces acting on the body and the net torque produced by these forces are not necessarily equal to 0. Then the first type of equilibrium can be described as follows. If the body under the influence of the net force and torque returns to its original equilibrium position, generally after some small oscillation about it, then the rigid body is in stable equilibrium. A typical example of such a situation is a ball at the bottom of a bowl. If the ball is displaced slightly, then it will roll back to the bottom of the bowl, that is, it will return to its stable equilibrium position. The second type of equilibrium describes a different outcome of the same initial situation. If the displaced rigid body does not return to its original equilibrium position, but moves away from it under the influence of the forces due to the displacement, then the body is in unstable equilibrium. By using the example of the ball on the bowl, we can place the ball at the top of the inverted bowl. If the ball is balanced at the top, then it is in equilibrium. However, any slight displacement causes the ball to roll down from the top of the bowl, indicating that its equilibrium position is unstable. The third type of equilibrium is perhaps the simplest one. If the displaced rigid body remains in its new position, then it is in neutral equilibrium. The ball lying on a flat surface is in a state of neutral equilibrium, since it will remain at rest even if it is slightly displaced, or it begins to move, settling in the new position if it is pushed slightly to roll. The new position of the ball is a neutral equilibrium position as well. In principle, the equilibrium of a mechanical system is stable, if the displacements in the system due to any sufficiently small interference also remain small. We have illustrated the 3 types of equilibrium with a ball, and any rigid body can be used as an illustration if the unconstrained force acting on the body is only its own weight. For example, we can suspend a ruler at 3 different points denoted by P as seen in the figure. In all the 3 cases the ruler is in equilibrium because its center of mass C is on the vertical line passing through the point of suspension P, and the weight g of the ruler is compensated by the constrained force F' due to the suspension. The equilibrium of the ruler is stable, unstable or neutral depending on whether the center of mass C is below, above or at the point P. However, this criterion is not general enough since the equilibrium of the ball used in the first example can be stable, unstable or neutral, although the center of mass of the ball is above the contact point between the ball and the surface in each case. The following criterion is still valid for both of the examples. By supposing that the unconstrained force acting on a rigid body is only its own weight, we can state that the body is either in stable or unstable equilibrium if its center of mass is in the lowest or the highest possible height. As a result of a small displacement from the stable equilibrium, the center of mass of a rigid body rises and a positive work Wg is done against the gravitational force, which increases the potential energy E pot of the body. At a stable equilibrium position, the body has therefore less potential energy than at any neighboring position occupied by the body after a small displacement. The opposite is true for the unstable equilibrium of a rigid body, where the center of mass of the body is lowered due to a small displacement of the body from its equilibrium position. Then the work done against gravity is negative, and so is the change in the potential energy, indicating that the potential energy of the body is greater at its unstable equilibrium position than at any neighboring position. In this form, the criterion can be generalized as a theorem which was stated by Lagrange in 1788 and proved by Dirichlet in 1846. The Lagrange-Dirichlet theorem states that the equilibrium position of a conservative mechanical system is stable if its potential energy assumes a local minimum in this position. In fact, the theorem only provides a sufficient but not necessary condition for stable equilibrium of a rigid body, that is, one can construct a conservative mechanical system where the potential energy has no local minimum in stable equilibrium. However, the converse of the theorem also holds for the examples from everyday life discussed here. By applying the example of the ball and the bowl, we can illustrate the theorem for the potential energy E pot of the ball as a function of the position of the ball rolling in the bowl. If we choose the bottom of the bowl as the reference level for the potential energy of the ball, then E pot is equal to 0 in equilibrium. For any displacement, the center of mass of the ball reaches a position where its height is greater than 0. Since the potential energy of the body is directly proportional to the height of the position of its center of mass, E pot is greater than 0 everywhere in the vicinity of the equilibrium position. As a result, the potential energy of the ball has a local minimum at the equilibrium position, which means it has a stable equilibrium there. If the ball is balanced on the top of the upside-down bowl, the potential energy E pot of the ball has a maximum at the top of the bowl because the height of the position of its center of mass attains the maximum. For any small displacement of the ball rolling over the bowl, the center of mass of the ball approaches the reference level. As a result, the potential energy of the ball is less than the maximum attained on the top of the bowl, and the ball has an unstable equilibrium there. In the case of neutral equilibrium, the ball can roll over a horizontal surface and its center of mass has a constant distance from the surface. Then the potential energy of the ball remains constant and the ball is in equilibrium at any position, which is a neutral equilibrium. For the sake of clarity, the reference level of the potential energy is set to be a non-zero value in the third figure. Without following the strict method elaborated by Dirichlet, we only give a sketch of the proof of the Lagrange-Dirichlet theorem. When we studied the dynamics of conservative mechanical systems, we saw that the force F acting on a point mass is given by the negative gradient of its potential energy E pot. This relationship also holds for rigid bodies under the influence of gravity, where the force F is the net force acting on the body and its potential energy can be determined from the position r of its center of mass in the gravitational field. Let the position vector r0 denote the equilibrium position of the rigid body. In equilibrium, the body is at rest and the net force F acting on it vanishes. As a result, the gradient of the potential energy of the body is equal to 0, that is, E pot has an extremum at the equilibrium position r0. We can approximate the net force acting on the rigid body by expanding the force F at a point in the vicinity of the equilibrium position r0 given by the vector sum of r0 and delta r, where the length of the displacement vector delta r is small. If we substitute the negative gradient of the potential energy E pot into the net force F, the Taylor expansion can be written as minus the gradient of E pot evaluated at the point r0, minus the second order derivative of E pot evaluated at the point r0, times the vector delta r, minus the terms of higher order in vector delta r. The first term in the right-hand side just gives the net force F acting on the body at its equilibrium position r0, which is equal to 0. We can approximate the force acting on the body up to the first order of its Taylor expansion by neglecting the terms of higher order. Then we only need to examine the sign of the second-order partial derivative of the potential energy with respect to the position r evaluated at the equilibrium position r0. If the second-order derivative of E pot is positive, then the potential energy of the body has a local minimum at the equilibrium position r0. For a negative second-order derivative, the potential energy has a local maximum at the equilibrium position. If the magnitude of the derivative is denoted by the positive constant k, then we can approximate the force F acting on the displaced body as minus or plus the constant k times the displacement delta r, depending on whether the potential energy of the body has a local minimum or maximum at the equilibrium position are zero. In this result we immediately recognize the law of force introduced in the discussion on simple harmonic motion. In the case of the local maximum of the potential energy, the force F is approximately equal to minus k times the displacement delta r, which is Hooke's law stating that the force is a linear restoring force accelerating the body in the direction opposite to the displacement and towards the equilibrium position. Since the length of the displacement vector delta r is small, the displaced rigid body undergoes a small harmonic oscillation about its equilibrium position. Normally, in realistic mechanical systems frictional or drag forces are also exerted on the oscillating body near equilibrium and the body will dissipate its energy. Due to the loss of energy, oscillating systems have a decreasing amplitude in time, that is the body performs a damped oscillation and eventually comes to rest at the equilibrium point. This behavior shows that the equilibrium of the body is stable if its potential energy has a local minimum at the equilibrium point. In the case of the local maximum of the potential energy, the force F is approximately equal to k times the displacement delta r, which is the other form of Hooke's law stating that the force F is a linear accelerating force and it accelerates the displaced body away from the initial equilibrium position. Then we talk about an unstable equilibrium if the potential energy of the body has a local maximum at the equilibrium point. We note that damped oscillating systems are not conservative and do not have potential energy associated with them. As a result, the equation of motion for damped oscillations must be derived from the fundamental equation of dynamics by applying Hooke's law. We can use this theorem to explain the motion of any rigid body displaced from its equilibrium position. For example, if we glue a relatively heavy fridge magnet to the inner side of a toilet paper tube and place the tube in the position on an inclined plane as seen in the figure, then it will be able to roll upward. Since the height of the common center of mass c of the weight and the tube decreases while the tube is rolling upward, the potential energy of the whole body decreases as well and attains a local minimum where the center of mass reaches its lowest possible position. Similarly, a vertical stick can be balanced on a horizontal support but it still have an unstable equilibrium because its center of mass c is above its point of support. When slightly disturbed from its position, the stick will fall down and not come back to its original position. Since the height of the center of mass of the stick decreases when the stick deviates from its vertical position, the potential energy of the stick also decreases. Consequently, the potential energy of the body has a local maximum at the vertical position of the stick. By attaching two relatively massive balls to the stick as seen in the figure, we can bring the center of mass c of the stick and the balls under the level of the support point of the stick. Then any deviation of the stick from its vertical balance position would increase the height of the center of mass and in turn the potential energy of the whole system. The equilibrium position of the stick therefore becomes stable if the stick is supplemented with the two balls. In the discussion on the conditions for stable or unstable equilibrium of rigid bodies we always talked about the local minimum or maximum of the potential energy. Indeed, in many cases rigid bodies can have more stable and unstable equilibrium positions depending on their shape and the distribution of their mass. For example, a homogeneous solid cuboid at rest on the horizontal surface of a table is in a stable equilibrium position. Since the solid body has 6 sides, it has 6 stable equilibrium positions as well. However, the cuboid can also be balanced on its 8 vertices and 12 edges, at least in principle, and these positions can be considered as 20 unstable equilibrium positions of the solid body. This demonstrates that only the neighboring positions of the given equilibrium position are relevant in the classification of equilibrium, and we restrict our examination to the local extrema of the potential energy of a rigid body displaced from its equilibrium position. So far we always considered the effect of gravity on rigid bodies in the discussion on their state of equilibrium. Now we present 2 examples illustrating the equilibrium of a physical system where the gravitational force is not relevant. The first example is a ping-pong ball attached between 2 identical springs of negligible mass as seen in the figure. If we stretch the springs then both of them will pull the ball by exerting forces on it, which are equal in magnitude and opposite in direction. As a result, the net force acting on the ball vanishes and the ball remains in equilibrium. For a small displacement of the ball either in vertical or horizontal direction, the ball will return to its equilibrium position with or without a damped oscillation, due to the restoring forces applied on the ball by the springs as Hooke's law states. Then the state of the ping-pong ball between the stretched springs can be described as a stable equilibrium. If we compress the springs then both of them will push the ping-pong ball by exerting forces on it which are equal in magnitude and opposite in direction. In this case the resultant force also vanishes and the ball stays in equilibrium. However, for any displacement of the ball in the vertical direction, the springs exert an accelerating force on the ping-pong ball and push it in the direction of the displacement. The state of equilibrium of the ball between the compressed springs is therefore unstable. The next example is not a purely mechanical system since electrostatic forces play the role of the spring forces of the previous example. We can place an insulating rod with a small metal sphere attached to both ends between the two electrodes of a planar capacitor as the figure shows. The rod is suspended on a low friction mounting which allows the rod to spin around its midpoint. If we charge the metal spheres with the same but opposite charges and place the apparatus in a uniform electric field E between the two electrodes, then it behaves as an electric dipole in the electrostatic field. The electric field represents the electrostatic force acting on the charged spheres. It accelerates the sphere with positive electric charge in the direction of the field and the sphere with negative electric charge in the opposite direction. Consequently, a force couple is exerted on the dipole with a torque which attempts to align the dipole to the straight field lines. At the same time, the body starts to oscillate about its rotation axis due to the inertia of the system of the road and the spheres. It is obvious that the dipole is in equilibrium when the lines of action of the electrostatic forces equal in magnitude but opposite in direction pass through the center of rotation. In other words, the torque vanishes when the dipole is aligned to the field lines and it is at rest. If the dipole is aligned such that the spheres are closer to the electrodes having the opposite charges, then the force couple point outward from the rotation center. Any displacement of the spheres causes for the dipole to perform a damped oscillation before returning to its equilibrium position. This behavior shows that it is a stable equilibrium of the dipole. If the dipole is aligned such that the spheres are closer to the electrodes having the like charges, the dipole is still in equilibrium. However, the force couple acting on the spheres points inward to the rotation center, and any deviation of the dipole from the direction of the electric field produces a torque rotating the dipole through 180 degrees about its midpoint. Then the dipole will perform a damped oscillation before finally returning to the stable equilibrium state. This result shows that the dipole in its initial state was in an unstable equilibrium. These examples illustrate that the concept of equilibrium and its classification into stable, unstable and neutral equilibrium can be introduced for any physical system whether gravitational, harmonic or electrostatic forces acting in the system. The state of equilibrium is also an important concept in thermodynamics or statistical mechanics. We have seen that the equilibrium of rigid bodies can be stable, unstable and neutral. However, we can also test how stable is the state of equilibrium and measure its stability with different quantities. A body at rest on a horizontal surface or standing or at least three legs is in stable equilibrium, if the vertical line passing through the center of mass C of the body also passes through the surface determined by the points of support, for example the triangle determined by the support points of three legs. This condition holds for the cuboids in the first two examples shown here, but it does not hold for the inclined solid body in the third example. For the inclined body, the line of action of its weight given by its mass m times the gravitational acceleration g does not intersect the surface of support of the body. Although both the cuboids are in stable equilibrium, it is evident that the equilibrium position of the first cuboid is more stable than the one of the second cuboid. The measure of the stability for such equilibrium states can be determined by the tipping or tilting test of the given rigid body. Its geometric measure with respect to the edge E is the tipping angle alpha defined by the maximum angle through which a rigid body in a given state of stable equilibrium can be tilted without tipping over. Since the body reaches the state of unstable equilibrium closest to its original state of equilibrium at the tipping angle alpha, it is a critical angle where the center of mass C of the body is directly over the tipping edge E. The energetic measure of the stable equilibrium of a rigid body is given by the work done while the body is tilted from its stable equilibrium position about the tipping edge E through the tipping angle alpha. If the increase in the height of the center of mass C is equal to delta H, then the work W done against gravity is given by the mass m of the body, times the magnitude of the gravitational acceleration g, times delta H. The dynamic measure of the stable equilibrium of a rigid body is given by the minimum force F acting at the center of mass C with a vertical line of action that is needed to tip the body over the edge E. All the three measures show that the greater the area of the support surface and the lower the center of mass of a rigid body are, the greater the stability of the equilibrium state of the body is. An equilibrium state of small stability is also called metastable. For example, the body shown in the middle figure is in the state of metastable equilibrium. For small deviations from its vertical position the body still returns to its equilibrium position, but it is also a relatively small tipping angle.